Hey everyone, and welcome to today's Explainer. I am so thrilled to have you here. If you love taking complex technical concepts and just completely breaking them down to see exactly how they tick, well, you are definitely in the right place. Today, we're going totally under the hood. We're going to decode an AI-generated Python script that was built specifically for real-time audio routing and digital signal processing. It is honestly fascinating how just a few lines of code can instantly turn your computer into a live audio effects processor, taking in microphone input, mathematically altering it on the fly, and blasting it out of your speakers with literally zero noticeable delay. Okay, let's dive into this. So here is a quick roadmap for our tour today. We'll start with the initial AI coding prompt, move into setup and configuration, then actually build out the DSP engine, and finally, we'll flip the switch and run the stream.
Let's kick things off right at the beginning, the AI coding prompt, which is essentially the blueprint for our entire engine.
Looking at the specific language used to prompt the Gemini AI, you really have to notice the dual goal here. The prompt specifically asks for a Python sketch to choose and route audio devices for real-time playback from mics to speakers, but also to apply DSP tasks at the exact same time, right? It's not just about recording a file and playing it back later like a voice memo. It's about live routing, grabbing that audio in real time and simultaneously applying mathematical transformations to it before it ever even hits the speakers. That at the same time requirement, that's exactly what makes real-time audio processing such a unique and frankly demanding challenge. Now, before we actually start looking at the code's dependencies, let's make absolutely sure we're crystal clear on a core term here, DSP, or digital signal processing. When audio comes into your computer from a microphone, it's immediately converted into a stream of digital numbers. DSP is simply manipulating those numbers mathematically to apply real-time tasks or effects. Think about it. If you make the numbers larger, you increase the volume. If you delay them and mix them back in, you get an echo. And that specific math is exactly what we are going to be building today. All right, so we have our blueprint. Let's move into setup and configuration and gather our raw materials. The AI provided a script that relies heavily on two primary Python libraries, and they divide the labor up beautifully. On one side, we have Sound Device. You can think of this as our logistics manager. It handles the audio input and output, physically connecting the microphones to the speakers. On the other side, we have NumPy. Now, NumPy is the heavy machinery on the factory floor. It handles all the intense numerical operations and the complex math required for the DSP effects. By strictly separating that audio routing heavy lifting from the actual math, the code stays clean, efficient, and most importantly, fast enough for real-time processing. Now, establishing the rules of our audio stream is absolutely crucial. And honestly, nothing is more important than this number right here, 44,100. In the configuration section of the code, the sampler rate variable is set to exactly 44,100. What that means is the computer is taking 44,100 individual snapshots of the incoming audio wave every single second. Let that sink in. It's the industry standard sample rate for CD quality audio, and it dictates exactly how incredibly fast our DSP engine needs to work just to keep up with the incoming stream. But having a sample rate doesn't really mean much if the code doesn't know where to look for the sound in the first place. The script uses variables for input_device and output_device. The AI notes that you're going to need to adjust these dynamically based on the actual names of your specific audio gear. To find those names, you simply run the command spd.query_devices. It'll spit out a list of everything plugged into your machine, which allows you to lock your code directly onto your specific USB mic and your preferred desktop speakers.
Okay, time for the main event. Let's build the DSP engine, our continuous audio assembly line.
The absolute beating heart of this script is a callback function named audio_callback. I really want you to picture this function as a continuously moving conveyor belt that operates in 3 distinct rapid-fire steps. Step 1, it receives a block of incoming audio samples packed neatly into an array called indata. Step 2, it applies the DSP processing by passing that data straight over to our apply DSP function. And step 3, it instantly writes that freshly processed audio to the outData array, shooting it straight out to the speakers. This whole loop happens over and over, thousands of times a minute, without you ever noticing even a fraction of a pause. Let's actually slow down a bit and zoom in on that middle step, the apply_DSP function. The AI designed a really slick, simple echo effect just to demonstrate how this works, and the foundational variable for this entire echo is 200, specifically a 200 millisecond delay.
The code actually calculates how many individual audio samples make up 200 milliseconds by taking 0.2 and multiplying it by our sample rate of 44,100. This tells the code exactly how far back in time it needs to reach into the audio stream to perfectly create that echo. And here it is. This is the exact line of Python where the magic happens. Let's break down this NumPy math, because it is beautifully simple when you look at it. It basically says the output data is going to equal 70% of the original raw input data. That's the 0.7 times in data part. Then, it adds in 30% of a delayed version of that exact same audio. It creates that delayed version using np.roll, effectively shifting the incoming audio data backward by those specific delay samples we just calculated. So you end up with a loud original signal mixed seamlessly with a quieter, delayed signal. Boom! You've just manufactured an echo using basic algebra. And it's honestly mind-blowing to think that Python is doing this math on tens of thousands of numbers every single second without even breaking a sweat. All right, the engine is fully built. Let's move on to connecting the pipes, running the stream, and flipping the switch. To orchestrate this entire machine, the main execution block of the script uses an object called sd.stream. Now, this is our master conductor. When you call sd.stream, it grabs your configured input and output devices, locks in your sample rate, and most importantly, it tells the system to continuously run that audio_callback conveyor belt we talked about a minute ago. The script then uses a very simple Python input command, printing press enter to stop the stream. This gracefully pauses the main program while the audio stream just runs endlessly in the background, only ever shutting down the factory when you finally decide to press the enter key. To wrap up the mechanics here, the source actually provided a great, actionable summary checklist to execute this on your own machine. Step 1. Just install the libraries via your terminal with pip install sound device, numpy. Second, adjust your specific device names in the configuration block so it knows what hardware to use. Third, and this is the fun part, you can modify the DSP function, maybe change the delay time or tweak that 70-30 volume mix. And finally, just run the script. If you speak into your microphone, you're going to instantly hear your own voice echoing out of your speakers. And honestly, that brings us to a really exciting question. We've just mapped out this entire blueprint together. We've seen exactly how NumPy math can create a simple echo within a live continuous stream. But as the AI pointed out in its explanation, you can completely replace that apply_DSP function with entirely different algorithms. So now that you understand how to control this DSP conveyor belt, what are you going to build? Are you going to write math for frequency filters, maybe massive auditorium reverbs, or even real-time pitch shifting? The whole framework is right there, just ready for you to experiment. Thank you so much for joining me for this explainer. Keep learning, keep building, and I will catch you next time.